We'll talk about boilers, waste heat boilers and CO boilers. Boilers have been in the industry for more than 400 years. One of the first equipment which was invented by James Watt several hundred years ago. So as far as boilers is concerned, everybody knows about boilers. But we will focus today on CO boilers and waste heat boilers. Before I start, I want to take a couple of minutes about talking about our company. Next year we will complete 30 years in business. We started in March of 1996, so next year we will complete 30 years. And currently, our main office, which used to be in US, has moved to India. And for almost 20 years, we are operating from India. The project office, the sales office is in US. Our technology, our focus has been innovation. And we have 3 patents currently, which we use mostly for fire heaters. Split flow for reducing pressure drop, increasing capacity, increasing efficiency. Inclined firing technology for reducing tube metal temperatures, again for increasing capacity of heaters. And then smart stack dampers for controlling draft in the furnaces. As I said, our model is based on providing unique value-added solutions. And we work directly with owners and end users. It's almost like a doctor-patient relationship. So we work directly. And our mission is improving the performance and efficiency of existing fire heaters and CO boilers. So let's start with very basic. We will quickly go over some of these basics. A boiler is an equipment where you produce steam, that's basically, or hot water actually sometimes. And the heat is provided by burning fuel, mostly fossil fuel like gas, oil, coal. We can talk about 3 major components of a boiler. The first one is the burner, which is providing heat to the boiler, converting chemical energy in the fuel to the thermal energy in the flue gases. Then we have heat transfer area, water valves or tubes, which absorb heat from the flue gases and transfer it to the steam or to the boiler feed water. And once that is done, we have stack or chimney which releases exhaust flue gases safely to the atmosphere. So these are the 3 major components of any boiler. There are typically 2 types of boilers, fire tube boilers and water tube boilers. In fire tube boilers, we have the flue gas flowing into the tube side and shell side has a water, and we have a sketch over here. Most of the time, these are used for low pressure steam applications. In refinery, we focus mostly on water tube boilers, where the water is on the tube side and flue gases are on the shell side. And these type of boilers are used for generating medium to high pressure steam in the industry. When we talk about waste heat boilers, the waste heat boilers, as the name suggests, is used for recovering excess heat or waste heat from flue gases. Typically, waste heat boilers will have 3 sections. We will have boiler feed water coils, steam generator coils, and steam superheater coils. And these are used for generating saturated steam or superheated steam. This is a picture of a HRSG, actually, kind of a waste heat boiler or thing. So need for waste heat boilers. My colleagues have put together these 2 statements where it says almost 20 to 50% of the industrial energy or heat is lost as waste heat. So there is a tremendous amount of potential for recovering waste heat and converting into useful heat. And the second thing is the CO2 emissions, the greenhouse gas emissions. They have reached a peak, or they keep on increasing every year, and we need to bring them down. And waste heat boilers could be an important equipment to reduce the temperature and reduce the fuel usage. So once you reduce the fuel usage, we will have less CO2 emissions. So they play an important role. When we talk about waste heat boilers design parameters, how do we design it? We're talking about a few parameters which we have to collect first. Heat duty in megawatt or million BTUs. What is the flue gas source? What is the composition of flue gas? The boiler feed water temperature and pressure conditions. What type of steam we are generating, whether we are generating saturated steam or superheated steam. And then from the flue gas side, we are talking of flue gas pressure drop. In most of the boilers, we will be looking at putting an ID fan or using the FD fan to provide for the flue gas pressure drop. In fired heaters, we are looking at ID fan or stack to take care of the flue gas pressure drop. Fuel sulfur content is also very important, and we will talk a little bit more in the following slides. The last point is most important: total installed cost versus annual fuel savings. So most of the owners are looking for 3 to 4 years of payback, that whatever investment they make, it should be paid back in 3 to 4 years. In US, it is very difficult to justify these projects because of very low cost of fuel. I think in Europe, Asia, and other places, the fuel cost is high, and it is a lot easier to justify most of these projects. Feel free to ask me any question if you feel like, or we can discuss it in the end. Economizer. The purpose of economizer or boiler feed water preheating is to recover the heat at the low end, and the boiler feed water offers the best potential because it has the lowest temperature in the whole system. The feed water temperature is usually about 110 to 160 degrees centigrade, and we can use a water side velocity of anywhere between 1 to 2 meters per second. Fuel gas firing, we use serrated fins. Fuel oil firing, we use bare tubes or fins. So a couple of things I want to talk about economizer is, in the industry, especially in the boiler industry, it is very common to use small tube sizes. And the reason they use small tube sizes is because it offers the most economical design and most efficient design actually in terms of heat transfer surface, because the heat transfer is inversely proportional to the diameter of the tube. But on the flip side, when you have small tube sizes, the distribution of boiler feed water becomes critical actually. You have to make sure that if you have got 26 passes or 36 passes, all the passes are receiving same amount of boiler feed water. And that has been a problem especially in your Rijeka CO boiler. And we have seen it in other CO boilers. I have a case study I will be presenting over here. So you have to kind of do, when you use small tubes, nothing wrong in that, but you have to kind of make sure that you provide enough pressure drop into the system so that the boiler feed water is uniformly distributed along all the passes. This is a a table showing or performance showing the with and without economizer, that with economizer the flue gas temperature is about 600 degrees F, and with economizer we can reduce it to 422 and basically get an improvement of about 6%, 5.5%. So economizer does play an important role when it comes to low temperature heat recovery. Dew point corrosion, I want to talk about because that's a very common issue in most of boilers. And this happens because almost all the fuel gases or even fuel oils or fossil fuels have some amount of sulfur present. Even natural gases or refinery fuel gases will have some sulfur present. EPA talks about 120 ppm of H2S as the limit in US. And what happens is when we burn these fuel gases, most of the H2S or sulfur compounds are converted into sulfur dioxide. But anywhere between 3 to 6% of that sulfur dioxide is also converted into sulfur trioxide. And it is this sulfur trioxide which is the most problematic component. So if you see my table, if there was no sulfur in the fuel gases, the dew point will be around 130 degree F or about 60 degrees centigrade. So that means you can cool the flue gases all the way to about 80, 90 without any fear of condensation if sulfur was not present. But the sulfur trioxide, what it does is it raises the dew point of the flue gases substantially, and the number is anywhere between 250 to 300, as you can see over here. And with that, we cannot cool the flue gases down to 250 or 300 degrees centigrade or even in those levels, because the sulfur trioxide condenses, forms dilute sulfuric acid, and dilute sulfuric acid is one of the most corrosive acids what we have seen. So that causes problems. So we had to make sure that whenever we are designing these equipment, we do not we have to make sure that there is no corrosion taking place in the economizers. What are the factors affecting the acid dew point? It's a sulfur content. Higher sulfur content will lead to higher dew point. Higher oxygen content will also lead to higher dew point. In fact, if you can get down to 0%, then hopefully there will not be any SO3 and your dew point will be very, very low. Water content in flue gas is also aiding in acid dew point. You can see that's why the fuel gas has higher dew point as compared to fuel oil for the same sulfur content. Vanadium in fuel oils. Fortunately, we have stopped firing fuel oils in refineries, but vanadium is also a catalyst for converting SO2 to SO3, so that also raises the dew point. Quick guidelines, general guidelines to avoid acid condensation is you keep the minimum metal temperature 25 degrees F higher than the dew point. And the stack temperature should be at least 75 degree F or 40 degrees centigrade higher than the dew points. And these guidelines will ensure that you don't get into corrosion of acid dew point. Next comes the steam generation section. And here we are taking the saturated boiler feed water from the steam drum and bringing it down through downcomers and then heating it up in the risers where only latent heat is transferred. There is no change in temperature. The boiler feed water gets converted into steam. In these cases, most of the time we will have bare tubes in the beginning and the hot zone, and then we will have extended surface tubes. We can have fin tubes in the lower temperature zone. So that's typically how the design is done. One of the common issues or the problems which happen in the steam generator coils is basically called the DNB or film boiling. Most of the designs will have the water wetting the tube surfaces all the time, and that's really good, if you have the water liquid wetting the tube surfaces. But if you have very high heat fluxes or low velocities, you can have steam blanketing the tubes, and that can start causing hot spots and problems in the boiler. So you have to make sure that you don't get into film boiling. Another issue which we have experienced is a slug flow, because it's a two-phase flow occurring in these coils. It's most common in forced circulation designs, not in natural circulation, but it can happen that you have slug flow, and because of the slug flow you can start having liquid pockets and then vapor pockets, and wherever you have vapor pockets you can start getting failures. So in most of the designs, boilers, we don't go for full vaporization of steam to boiler feed water to steam. What we do is to prevent film boiling, we put excess circulation, and whatever is coming out of the steam generator coils is a mixture of steam and water. And then we have a steam drum where they get separated, and then the water gets recirculated and steam is sent out to steam superheater coils or to the header. So that's generally how these coils are designed. There are two designs which are common. We're talking of natural circulation and forced circulation. In low pressure boilers you keep high circulation rates. In high pressure boilers you keep lower circulation rate. It's good actually. So that's generally how we do it. This is a natural circulation design, and in natural circulation we are using the head of water, or the density difference between the downcomer and riser to ensure circulation. So there is no pump, and these circulation rates are very high, typically about 20. They have low pressure drop, so anywhere between 20-25 is what we kept, so that way the steam which is coming out of these coils is only 4 to 5%. So that's the design we have. We have a steam drum on top, mud drum on the bottom. These are the downcomers, and then we have, these are the downcomers and these are the coils preheated. Another thing I want to talk about is whenever you are having steam generation, vertical tubes is a preferable design because it offers release of steam. The steam keeps on escaping to the top, Whereas in the horizontal tubes, it is little difficult. So what we do in the horizontal tubes is we have co-current designs. That means the flue gas is flowing up and the boiler feed water is also going up, so that the steam can be released, And what industry has seen is if you provide 10% incline to the horizontal tubes, it improves the performance of those steam generator coils drastically. That's what typically happens. But for forced circulation, we normally CO boilers, we normally use horizontal tubes because of the construction, otherwise the construction will become very complicated. So these are some of the advantages and disadvantages of natural circulation. Mostly vertical tubes is what we have, and the steam drum has to be provided on a higher elevation to give the design. This is forced circulation. What we do is we take a pump and then connect it to the steam drum, provide enough NPSH, and then it kinds of circulates the boiler feed water. 10:1 is on the high side. Generally 8:1 or even 5:1 is used in forced circulation. We can still get good designs out of forced circulations. These are some of the advantages of forced circulation. Quick startup, you can use horizontal tubes, small plot requirements. Steam drum location is not restricted. There is no requirement of very big head, but there are some downsides of pump maintenance and spare pumps, those other type of things. And next we come to the steam superheater coil, and steam superheater coil also susceptible to failures actually. And the reason for that is when you're talking of steam superheater coils, now we are sending gases, the vapor steam in these coils for preheating, and when you send vapors, the whole situation changes. In the Economizer coil, we were sending liquid and liquid in, liquid out, very high heat transfer coefficient. Steam generator coils, we were sending liquid in and liquid plus vapor out, even higher heat transfer coefficients. But when we come to the steam, the heat transfer coefficient goes down drastically, and as a result of that, we can have high tube metal temperatures. Overheating of these steam superheater coils is very common, and most of the failures happen in high temperature steam superheaters is due to high temperature, so burnout. So that's typically how you have to be careful. You have to give more pressure drop so that you have higher velocities of steam inside the steam superheater coil, and you can get a better heat transfer coefficient in your coils. And then we have a steam drum, which again forms a very important component of steam systems, whether we are talking of waste heat boilers or any regular boiler also. And steam drum is an important component because it separates the steam from water. It also provides for emergency water, for if in case the pumps fail, it can give us about 2 to 3 minutes of this thing. There are instrumentation connections to monitor the steam drum, blow down facilities, chemical injection facilities, overpressure protection, safety valve. So steam drum is a pretty important equipment in any waste heat boiler. It does a lot of functions. So let's talk now about the CO boilers. You must be wondering, I've spent 25 minutes on the basics, but I had to do it. Let's talk about the FCC fluid catalytic cracking unit, CO generation. In these, flue gas is formed during the regeneration of the catalyst when the catalyst is burnt to remove the carbon. Flue gases are formed. There are two types of processes. One is the full burn, which I think is the recent process, where all the carbon which is burnt is converted into CO2. And in those cases, we call the CO boiler or call it more like a flue gas cooler actually, rather than a boiler actually. And the second one is where partial combustion takes place. Historically, I think most of the units in the beginning were partial combustion. So they all had CO boilers where the CO was burnt in a combustion chamber or was burnt in a boiler to destruct the CO, recover the heat. That's typically this thing was done. So these gases which are generated from regenerator have a pretty high temperature, anywhere between 500 to 750 degrees centigrade. The pressure could be anywhere between 1.5 to 3.5 bars. And the waste gas flow rate, it depends on the FCC unit capacity, but all the way up to 700,000 kgs per hour. It could be anywhere between 50,000 to 700 kgs per hour, 1000 kgs. So this is a flue gas cooler. Norbert, this is from your plant. So this is a natural circulation boiler with vertical tubes. Flue gas is entering at 700 degrees, leaving at about 300 or 350 degrees centigrade. There is no combustion taking place, and a lot of people say, hey, let's just call it a cooler instead of a waste heat boiler. We have the steam superheater coils, then we have 3 banks of steam generator, and in the end we have an economizer section. So this is a natural circulation with vertical tubes. When we come to fired boilers, there are 2 types. One is conventional water tube boiler. So what industry has done is they have taken a standard water tube boiler and introduced a CO-rich flue gas in the radiant section of the water wall boilers. And again, you support it with the fuel gases to get the right temperature or the minimum firebox temperature. The second type of combustion chamber, of the CO boilers, what we use in the industry is combustion chamber with a convection bank. That is what you have in Rajika. Here we burn the CO-rich gases in the combustion chamber along with the fuel gases to get rid of all the CO. And these hot flue gases are then sent in a convection section type of design, boiler design, where we generate steam or preheat hydrocarbon feeds and then dispose it into the ESP and forward by the stack. Furnace improvements has done the both type of boilers, whether it's a CO boiler or the flue gas coolers. We are experiencing both types. So this is a conventional water tube boiler and FCC waste gas firing. We worked on it about 15 years ago. This was almost like 400,000 pounds an hour steam boiler. In fact, this was a CO boiler and we converted it into a natural gas fired boiler. This was at Phillips Borger, and they had converted their process from partial burn to full burn. So they did not need this boiler at all actually. So they had 2 options. They could either shut it down, junk it, or the EPA said you can continue operating it, but the NOx has to be brought down to 15 ppm. And the EPC, to whom they gave work, tried several options. Finally, they could not succeed. So they came to us and we worked on this project and converted this to a natural gas fired boiler and reduced the NOx down to 15 ppm using FGR and steam injection. So this was a very good and big project for us. And this is the second type of design, which is very similar to your Rijeka boiler. You can see this, we have a combustion chamber at the bottom. There are 6 burners here. This is the CO plenum through which the flue gas is injected. This is the combustion air plenum. And then we have the convection section over here, different services, steam drum is on top, and then it goes to the, in this case I think this was going to the SCR unit and then to the scrubber. That's the configuration which is more popular in US on the CO boilers, because they were all forced to reduce NOx emission. So they put SCRs and then they put scrubber to take care of the particles and other things. So CO concentration in these FCC units can range from few ppm, few hundred ppms to few percent, and we have to destruct the CO because we cannot vent CO into the atmosphere. CO is poisonous, so there is a limit of about 50 ppm. So what we do is we burn it and we use the supplementary fuel to raise the temperature of the flue gases to about 900 to 1000 degrees centigrade. So that's one requirement. Second is have a minimum residence time, and that residence time depends on the turbulence, the design. So anywhere between half a second to 1.5 seconds of residence time is recommended to destruct the CO. The other thing what we have done is, if the residence time is not available, we create good mixing of the flue gases and FCC waste gases so that the CO gets destructed. This is from another unit, the waste gas composition. You can see here it's very high, 3 to 12%, carbon dioxide, oxygen, calorific value can be 70 to 280 kilocalories per kg. The two things which I want to talk about is the sulfur content and the dust content. So sulfur is responsible for dew point corrosion and dust is responsible for fouling in the CO boilers. So that's the two things you have to take care and make sure that you don't get into dew point corrosion or fouling of CO boilers. We are not focusing on inside fouling. That's a very different topic and does not happen very often because water is generally very clean. If you maintain TDS within the limits, you should not have any fouling issues. But on the outside, you can have fouling due to soot, ash, catalyst dust, and that will reduce the heat transfer and efficiency. In the CO boilers, the heat transfer is controlled by the flue gases. So anytime you have fouling on the external surfaces, it will directly impact the heat transfer. So some of the indications are your flue gas temperature will start rising, flue gas pressure drop will start increasing also, the steam generation will come down, your steam superheater temperature may also come down. So these are some of the things which can happen when you have fouling. And the most important equipment to combat fouling is soot blowers. There are two types of soot blowers. We are not talking here about sonic soot blowers, but we are talking more about the steam soot blowers. In steam soot, the function is you blow high pressure steam, and that steam blows the dust, removes the dust from the tubes, or blows the dust or soot or catalyst from the tubes, cleans it, So that's the principle. There are two types of soot blowers. There are fixed rotary type, which have multiple nozzles, and these are used generally in low temperature zones. And then there are retractable type, which have a lance which is fully retracted when it's not working, but when it is working, it goes inside, produces a cleaning action by helical path, and is a lot more effective than the fixed rotary type. And we normally keep bays of about 18-inch clearance or 600 millimeter, sometimes 24-inch clearance for the soot blowers. This picture shows the soot blowers, retractable soot blowers installed in one of the convection sections. So that's a picture of a rotary soot blower, and these are the tubes, and this is the lance which is permanently installed, and there are lots of nozzles which kind of inject the steam into the convection section, and because of the high velocity, the catalyst dust or soot is removed. And in retractable, instead of having 10 holes or 20 holes, there are only 2 holes. So as a result, the velocity of steam is much higher and the range is also much better, but it is a little bit more complicated. So the lance comes out, goes all the way through the convection section, and then comes back. Excuse me. So we are talking of flue gases. What we have to kind of focus on is catalyst fines, and it's important we use retractable soot blowers only in this installation, because there is a lot of catalyst fines. And any time your temperature goes up by 25 degrees, you have to do soot blowing maybe twice a shift religiously, to keep the soot blowers clean. Another thing which is there is, if you have high velocity, the lot of dust, catalyst dust, will get carried away. So as you will see, we have increased the velocity in your CO boiler to minimize fouling to the extent possible. You have done that. These are some of the other problems in CO boilers. CO slippage, flue gas temperature, leaving the convection section, that's boiler feed water coil leakage, steam superheater temperature high, dew point corrosion, So these are some of the problems which are typically experienced in CO boilers. So one thing I want to talk about general is when we talk about boilers, and you will see in the industry, boilers are not process units. The moment you call boilers, it's not a process unit, it's a auxiliary, it's a utility. And generally, they are not expected to run 24 hours a day, 365 days a year, or for 5 years, what we are expecting our process units to run. And you will always have standbys, like if you will see you have 2 or 3 boilers in the refinery, so even if one boiler shuts down, the other boilers keep on working actually. And that's a misnomer when we talk about CO boilers. The CO boiler is expected to run continuously as a process unit. So that boiler name becomes like a misnomer, that maybe we have got a standby boiler. Whereas if you talk of process units, you will rarely see any standbys, they are designed for long running, and they are a lot more rugged applications than the typical boilers. So how did we get into CO boilers? We are fired heater people. We have done fired heaters almost for a long time. So it's almost like 25 years ago, we were approached by Mobil. There used to be Mobil at that time, not Exxon. Exxon came later. Exxon was a separate company. So Mobil had a CO boiler in one of their refineries, Beaumont, Texas. And they were changing the fuel gas composition in the CO boiler. They asked me, can you tell us the impact of changing the fuel gas composition on this CO boiler? And I had not worked on any boilers before that, but I decided to take up this challenge. I said, how will it be different? So we decided to take up a challenge and went ahead and modeled the boiler in the FRNC software. It took me some time in the first time, to about 2 months, but we were able to successfully model it. And then we realized we have a better rating capability than the boiler people themselves, So once we got that capability of modeling boilers, we were able to model them accurately. And I'm talking of the water valve boilers, and we could predict their performance. So that's how we got started about 25 years ago. This is a picture of that boiler. This has a steam superheater, water valve, roof tubes, steam generator bank, and the economizer actually. And this boiler was a tangential fired unit with burners installed at 4 corners. And then we had the CO burners also right next to the fuel gas burners. So I want to talk about a very similar case we did about 20 years ago. It's almost 23 years now. This boiler, CO boiler, is very similar to yours in Rijeka. And they were going to rebuild that boiler. So they came to us and said, can you help us redesign this boiler, because we have had several problems in the past. So we said, okay, we will look into it, and that's basically talking of the case study. So this boiler was originally designed in 1960, and this is one of the few boilers we have seen which had a CCU feed preheating coil in their boilers, And then it had about steam generation coils, and superheated steam was being generated at 45 bars and 400 degrees centigrade. Boiler feed water inlet temperature was about 110. Stack temperature design was 260, but it was operating for much higher. And again, designed for 100% auxiliary firing, just like yours. Mix of bare, studded and fin tubes. And this boiler had been revamped 3 times, just like yours. You had revamped it 2 times, but this was revamped 3 times, 1976, 1984, 1990. So just to show you the schematic of this boiler. So the combustion chamber was rectangular. They had 3 sets of 3 burners each, so they had about 9 burners. This was the air ducting. A part of it was going into the burners, and part of it was going directly into the combustion chamber. We had the CO plenum over here. This was the convection section, where the steam was being generated and the oil was being preheated. And then we had the flue gas going to the stack. Actually, they had again going to the ESP, then later on they changed the ESP to a scrubber and SCR. So this was the design or the configuration of the CO boiler original design. It had retractable soot blowers in the bottommost section, and then rotary soot blowers in the upper section, almost just like your Rijeka refinery. And there was a boiler feed water on the coil, then steam generator coil, then steam superheater coil, then oil preheat coil, and the bottom again had steam generator coils. So when we looked at the design, we saw several issues. The stud tip temperature in the oil preheating coil was very high. Similarly, the peak fluxes were very high. What was happening was the flue gas temperature leaving the CO heater, even though they said it's 260, we found out even for the clean case is 285, and for fouled case is about 343, so pretty high. They added steam superheater bank in 1984. They added steam generator tubes and changed the economizer design, They also added 3 rows of retractable soot blowers and increased the height of the convection section by 4 feet. So they did a major revamp, and this is how it was built in 1984. The height went up from 19 feet to 23 feet. They put retractable soot blowers all the way through and then modified the design. But even after modifying the design, they still had lots of issues. When we went into the unit project, they were having high steam superheater temperature. They wanted to eliminate the steam superheater just like you. Reduce the flue gas temperature, leaving the convection section. So that was almost similar. Reduce the coking rate in the hydrocarbon preheat coil. They were also getting tubes sagging in the heater. They wanted to upgrade the metallurgy of bottom steam generator coils. Keep existing soot blower location, they didn't want to change that. Flue gas outlet also they want to keep the same. And they wanted to go from studded tubes to low density thick fin tubes for better cleaning and lower pressure drop. So we came up with a design, and in the same height we were able to pack a lot more area, We were able to pack a lot more area. We did not change the retractable soot blower locations, we kept it same. But we made substantial improvements. We went up from 2 rows to 3 rows in steam generator. Then we had oil preheat coil. We added rows here. Then we reduced the number of rows in the steam superheater. The boiler feed water coil was split into 1 row over at here for the high temperature and then for controlling the acid dew point, and then it was counter current in the top section. So we made all these changes, and that's basically summarizing the changes, what was existing, what was revamped, So we did it. And same thing like yours, the design lacked properly positioned refractory corbels. They were also having flue gas bypassing just like yours. This design was also built by Foster Wheeler. So the vendor or the designer is the same in this project and your Rijeka project. So we were able to redesign and put properly positioned refractory corbels to eliminate the flue gas bypassing. And this is, we were able to eliminate the cold and corrosion, increase the FCC duty, eliminate flow distribution problems, and improve the boiler efficiency. And you can see how we were able to, even save them almost like $1 million per year. Increase the process duty, increase the total duty, So this refinery is short on steam, so they want every possibility to. Dust content is very important, and you need to use appropriate fouling factor for sizing these units. So this is another job which we did, and this also is a CO boiler for a Phillips in Linden, New Jersey. And this was this economizer coil in the CO boiler which was failing every few months. That is what they were having, every 2 months. So we looked at that design and we added restriction orifices to improve the flow, So this was very similar to yours, inlet header, and then, there were lots of passes. And we did the CFD of this unit, and you can see the flow was preferentially going through the central tubes, and all the rest of the tubes were suffering. So when we added restriction orifices, we were able to improve the flow pattern in almost all the passes. So this is the same boiler, and when we, I think 2 or 3 years down the road, they came to us and said we are having a CO slippage problem in the convections in the CO boiler of almost like 500 ppm. So this time we focused on the combustion of the CO boiler. So this is the CO plenum and these are the burners. That's the combustion chamber, rectangular combustion chamber. And they had a CO slippage taking place. So if you see, the FCC off gas was coming from the top. This is the actual picture of their boiler. This was the burner. And this is the air port, rectangular air port what they had. So this was the CO boiler what they had. And our job was to give them improvement, how to improve it. So we did two things. First of all, we said let us make sure that the CO is being distributed uniformly in the CO boiler, to all the burners. There are 9 burners. We want to make sure that all the 9 burners are getting the same amount of CO. So that was the first model we did. And when we made the model, we found that CO was varying very much. So we fixed that issue, We redesigned the CO plenum and put splitters to make sure that all the burners, even you can see over here, this is 7 and this is 13, This is 9, this is 11. So it was not uniform at all, So we made sure that we do that. And the second one we did is that this is the schematic that the CO gas is coming, FCC waste gas is coming from top. This is the combustion air and this is the air velocity. So this was the design what they had. We did the CFD and you can see the temperature contours. High temperature was mostly at the bottom of the combustion chamber. This is where the CO gas is coming in. So we were able to identify the problem, and this is the CO mass fraction. So the CO was going, unreacted. You can see over here, and we could see the CO slippage was more than 500 ppm over here. So this is the path lines. We can see the FCC inlet, airport, wind box, so we could, in CFD model, we could trace how these flue gases and different streams are mixing, or not mixing. So this is the modification which we implemented in their design. We worked on 5 or 6 different options, not just one, 5 or 6 different options, and after looking at all the options, we selected the minimum cost option, for the minimum investment. And what we said was the FCC gas was coming straight down. We told them, let us put it at 45 degrees, So we changed the inlet, put a splitter here, and then we put it like this, And then we also added a refractory baffle wall, something similar to what we have done in your case. So we added a refractory baffle wall over here. We did not change the burners or their combustion air supply because that would have been a very major modification. But that's what we did, So as you can see, when we did this, suddenly everything became, the CO was burning within this space only, not even going here, And you can see over here, the temperature contour became absolutely uniform, So we introduced a lot of turbulence in this area. And that kind of became like a mixing chamber. And that solved the problem of CO slippage, So you could see over here, And this is very similar to what we are doing yours, So we feel very confident that by introducing these baffles, mixing plate or choke plate, we are inducing turbulence, and with the turbulence we will be able to solve the CO slippage problem. So good mixing of FCC waste gas with air is required. Poor mixing leads to the CO slippage, and CFD is a good tool to use for monitoring this waste gas and combustion air. Dew point I have already covered, so